Okay, so we're going to now move into this topic of arc length and curvature. We've already been looking at space curves, and now we want to see how we can, for example, measure the length of a curve through 3D space. So I want you to recall this formula. We look at parametric curves on a plane back in Calc 2. This was the formula for the length of a planar curve. So you have like t going from A to B, right? And then, so what we're essentially doing, you want to remember, is you have like this starting point and this ending point. I'll just say t equals A and t equals B. And what you kind of do is I'm going to really over exaggerate this, but you're chopping it up into a bunch of little pieces. And what we're doing is we're taking seeing the change in you're making a bunch of little right triangles where you have the dx and the dy, dx over dt, then dy over dt, like the change in x and the change in y. And what you're doing is like just measuring this hypotenuse. And so what you end up with is a whole bunch of these little tiny segments, and all together. Now, of course, this is infinitesimally small segments, so it actually follows a curve, but this is very grossly exaggerated. You can kind of think of this as, in terms of a limit, as these. I actually should have put delta x over delta t, but at any rate, that's the idea. So then what you have is the arc length in 3D space for some vector function f of t, g of t, h of t. It's going to follow the exact same. It just extends to another dimension. So you're going to take in this integral from a to b, and it's a square root of dx over dt squared plus dy over dt squared plus dz over dt squared, and then you have the dt hanging on the end. And you can actually simplify this a little bit using vector derivative notation. This is actually the same as the magnitude of the first derivative of t dt. That's actually another way of writing this thing. So you take the derivative of the vector function r, and you calculate its magnitude and take an integral of that magnitude from a to b. Okay, now as an example, let's take this. We're going to look at the arc length along this helix, cosine t times I plus sine t times j plus t times k. So we're going to go from 1, 0, 0 to 1, 0, 2 pi. So in other words, t is going to be going from 0 to 2 pi. This is going to be one full rotation of this helix. And so we'll just evaluate this. The length is going to be an integral from 0 to 2 pi, where t is the variable of integration here. And what we have is the square root of the first component, the derivative squared, so that's going to be negative sine of t squared, plus the derivative of the second component, that's going to be a cosine of t squared, plus the derivative of the third component, which is just a number 1. And then I'll put this dt on the end. We'll clean this up a little bit, and you'll see it's not actually that bad, because this is the integral from 0 to 2 pi, the square root of, well, what's this? This is sine squared of t plus cosine squared of t. Sine squared plus cosine squared is 1. That's the Pythagorean identity. And so, in fact, this is just going to be the integral from 0 to 2 pi of square root of 2 dt, which in the end is just square root of 2 times 2 pi. Which, how would you write this? I guess you could write this as 2 root 2 times pi. That's fine. That's how many units long. So this is, you kind of start here and you're going around the helix one root, and so this is not 2 pi long. It's actually 2 times root 2 pi. So that's kind of how far this thing is stretched, in a sense. All right. So if the curve C is only traversed once, when t goes from A to B, so it doesn't like double back on itself, then the arc length function can be a function of t, which is to say what is the length between A and where we stop at time t. When from t equals A up to t equals some value t that we kind of pick. So it's going to be s of t, some function s of t, where s is going to be used often for the arc length. It's the integral from a to t of, we're going to use a change of variable so we don't have t's, because t is now a variable of integration. It's a bound. It's a variable bound of magnitude of r prime of u du, which we can write also as this integral from a to t, where we are taking the sum of these squared partial derivatives. Taking the sum of these squared derivatives times, and then the du at the end. So this is another way of writing this. And so what we're going to, the reason we're interested in an arc length is we may wish to parameterize the curve in terms of arc length rather than t. The reason being, you can actually define the same curve, the same exact curve in space, with different parameterization of t, where if you double the speed at which you traverse it, then it's going to change the function. But if you have the parameterization in terms of the length it's traversed thus far, it's going to be a unique parameterization of the curve. So the idea is we can then find the inverse t of s, and then we use this as the input into our vector function r of t. So let's take a look at an example. Okay, so let's take a look at this helix again. R of t is cosine ti plus sine tj plus tk. And so we wanted to reparameterize this in terms of arc length. Remember what we do, s of t is this integral from here. It's going to be from 0 up to t of this square root of, remember what it was when we did this in this derivative, actually it was 2. Remember, it was 1 plus 1 because we had sine squared plus cosine squared. So actually it's just the square root of 2, and then it was a du. So this actually comes out to be simply square root of 2t. So in other words, s equals square root of 2t. So t is going to be 1 over square root 2s. And so we can reparameterize this. R of s is going to be the cosine of s over root 2 I plus the sine of s over root 2 j plus s over root 2 k. So now we've reparameterized, and so as we increase the arc length, this will tell you exactly where you get to at any given point. So we'll define a couple of terms now. A parameterization of a space curve, r of t, we call it smooth on some interval as long as this first derivative is continuous. And we want to make sure that this first derivative is never anywhere equal to the 0 vector anywhere on this interval. Meaning, what that means is that basically the curve is only going to make like nice. This curve through space actually doesn't come to any corners or points, or make any sudden jumps in speed, something like that. So we say a curve is smooth if it has a smooth parameterization. So if there's a way you can parameterize this curve in space such that it is a smooth parameterization, then the curve, we call it smooth. And then it looks like we've been describing. No corners, no cusps, nothing pointy. So if you have a smooth curve, then its unit tangent vector is given by we call it capital T, remember? And it's the first derivative divided by the magnitude of the first derivative. And so if we're interested in how does the tangent vector change, if we look at how the unit tangent vector changes with respect to arc length, it would be independent of the parameterization that we're using. And then we call that curvature. Okay, so we define the curvature of a curve, kappa, which is actually kappa is a function of time, could be, or function, but the kappa at any given point on the curve, right, is going to be the absolute value of the change in it's the derivative of the unit tangent vector with respect to a change in a change in arc length, dt over ds. All right. So remember, if we find the derivative of the unit tangent vector with respect to t, we can actually express that as the dt over ds times ds dt. And so, in fact, if we wanted to find dt over ds, we can express this as dt dt divided by ds dt. And so we're going to redefine the curvature in that way. It can be written as the magnitude, or the absolute value of dt over dt, all of that over ds over dt. And because the ds over dt is actually just the change, the first derivative, that's a change in curvature with respect to change in So because ds dt, we just defined this as the magnitude of r prime. What we can write is the curvature can be written as the magnitude of t prime, which is with respect to t, over r prime. Magnitude of t prime of t over the magnitude of r prime of t. So this is another way that you can calculate the curvature. Okay, now let's consider a circle of radius a. We'll parameterize this x equals a cosine t and y equals a sine of t. And we can actually calculate the curvature of this two-dimensional curve, no problem. So what I want to find is what is the first derivative. And that is going to be, the first component is going to be the derivative of the cosine, which is negative a sine of t. The second one is going to be a cosine t. This is the first derivative. But I'm going to need to find the magnitude of this, right? And what is it? It's the square root of a squared sine squared t plus a squared cosine squared t, which is just the square root of a squared times 1, right? Which is just a. So to make this the unit vector, the unit tangent, I should say, the unit tangent vector is going to be 1 over a times negative a sine t and then a cos t. Right? To turn this is to say this is r prime of t divided by magnitude of r prime t, which is of course just negative sine t cos t. And let's find its derivative, t prime. We've got negative cos t, and then we'll have negative sine t. We're going to find this magnitude. The magnitude of this is, of course, the square root of cosine squared t plus sine squared t, which is just a big old 1. So what is the curvature? I said it's the magnitude of t prime of t over the magnitude of r prime of t. Well, this is the magnitude of t prime is a 1 divided by the magnitude of r prime is an a. So the curvature of a circle of radius a is 1 over a. So in other words, we're talking about as the, what is the change of like, of the how is the, we're kind of quantifying how fast does how fast does the tangent vector change with respect to a little bit of change in arc length. And you can see as the circle gets bigger, then the same small amount of change in arc length is going to have a smaller and smaller impact on the change in the unit vector, in the unit tangent vector. So the curvature can be expressed in this other way. This is a theorem that I'm not going to prove. You can look up the proof, but the curvature at time t is given by the magnitude of the cross product of r prime t cross r double prime t. And then this, and then that's divided by the magnitude of r prime cubed. So we're going to cube that. We'll look at an example. So we have this twisted cubic space curve. I'm going to find the first derivative, r prime of t, and that is pretty simple. It's 1, 2t, and then 3t squared. Get the second derivative. That's going to be 0, 2, and then 6t. And so what I want to do is find a couple things. I'm going to find the magnitude. I might as well do that right away. The magnitude of r prime t. I'm going to express it in terms of t. So this is going to be the square root of 1 plus 4t squared plus, that would be 9t to the fourth. I'm going to need that in the formula, and let's get a let's find the cross product of these two. So the cross product r prime cross r double prime is going to be I j k 1 2t 3t squared 0 2 6t. Okay, and so this is going to be we've got, let's see, we've got 12t squared minus 6t squared for the first component. For the next one, we've got 3t squared times 0, that's a 0, minus 6t. And then for the third component, we're going to have 2 minus 0. So that's just a, okay. So we've got 6t squared minus 6t and 2. What's its magnitude? The magnitude of r prime cross r double prime is square root of, let's see, that's going to be 36 t squared, or sorry, that's t to the fourth plus 36 t squared plus 4. All right, so altogether then we have the curvature at any at any t is given by the square root. Actually, yeah, I'll just leave it as in terms of two square roots. We've got the square root of 36 t to the fourth plus 36 t squared plus 4 all over the square root of, now this is going to be cubed, but I'll still write it out. I'm going to write it in this order, 9t to the fourth plus 4t squared plus 1, and that's cubed. So this is the curvature at any point, or at any time t. So for example, the curvature at time 0 is going to simplify to be the square root of 4 over the square root of 1 cubed, which is just going to come out to be 2. Okay, so if we are looking at a plane curve like y equals f of x, so where the curve that follows this function, we can let x be the parameter, and so we would actually, the r of t in this case, right, is going to be, it would be t, and then I guess we would say like f of t, kind of like that. And so when we work everything out, we end up This is the simplification of this. Now, if I would put actually x in place, right? I'm not gonna work it all out, but this is what the result would be. So the curvature for any x value is found by, you take the absolute value here. No, these are absolute values, not magnitudes. Absolute value of f double prime over the absolute value of 1 plus f prime squared to the 3/2 power. Let's take a look at what this what would be for an example. Let's let y equals x squared, and let's find what the curvature is for any value of x. So the curvature at some value of x, it's going to be, I'll just write this out in the formula, the absolute value of the second derivative would be 2, right? Because y prime is 2x, and then y double prime is just 2. That's what we have up in the numerator, and down below we'll have 1 plus 2x squared to the 3/2 power. So let's rewrite that a little bit. This actually is going to be 2 over, so this is, since 1 plus 2x squared is always positive, we can write this as the square root of 1 plus 4x squared cubed. Okay, so for example, the curvature at the point at when x is 0 is going to be 2 over 1, so that's just 2. The curvature at 1 is that's to say at the point 1, 1 is going to be 2 over, let's see, this is going to be square root of 1 plus 4 is 5 to the 3rd. Okay, and the curvature at 2, so this is at the point 2, 4, we're going to have 2 over square root of, let's see, it's 1 plus 4 times 4, that's 16, that's 17, root 17 cubed. So what we have then is the curvature of this parabola, like this is a parabola. At this point, it has the highest curvature. The curvature is 2. And then at this point here, I'm being a little bit not careful. Curvature is a little bit less than 2, right? It's lower, and here at this point here, the curvature is even less. So the idea is the curvature is actually it's decreasing, and in fact, you can actually interpret the curvature as the if you were to, well, actually, let's talk about that in a little bit. So we'll talk about the interpret curvature in terms of circles in just a bit. First, we have to define a couple other little things. So if we take a smooth space curve, r of t, we can get its unit tangent vector. And it turns out the unit tangent vector is orthogonal to its derivative, t prime. If we turn t prime into a unit vector, we call it the normal vector. N of t is just, it's t, the first derivative of t, so t prime, divided by the magnitude of t prime. Okay, so that's going to be called the normal vector. So we'll define the binormal vector as the cross product of the unit tangent vector and the normal vector, which by definition is always a unit vector. So one thing to point out, if you take two unit vectors, what these two, the tangent vector, tangent unit vector and the normal unit vector, these two vectors are they're actually orthogonal to each other, and so what we get is, by definition, then this binormal vector is a unit vector. The cross product of two orthogonal unit vectors is a third unit vector, which is orthogonal to the two of them. What we kind of have, I'm going to try to illustrate it a little bit. So you have this curve going through space. So suppose we have the tangent, the unit tangent vector might look like this, okay, and the normal vector would look like this, for example. And so the binormal vector would be, and I can't really draw it because it's like coming towards us. This would be where like the binormal vector would be, where it's making a right angle with both of them. Can you kind of picture that? Okay. So what we can do is we can we can use the tangent vector. So the normal vector is showing the direction in which the tangent vector is changing, and the binormal vector is going to be normal to this plane that contains the curve at that point. We'll show an application of this in just a second, but let's do a little bit of practice finding the normal vector and the binormal vector. Okay, so let's take a look at this helix again. So as you recall, the first derivative is going to be the negative sine of t I plus the cosine of t j plus k. And if you recall, this thing had the magnitude of r prime of t was square root of 2. We did this earlier on. And so the tangent unit vector, the unit tangent vector, is going to be you take the first derivative and divide it by its magnitude, and so it's going to be negative 1 over root 2 sine of t I plus 1 over root 2 cosine of t j plus 1 over root 2 k. We're going to now find its derivative. So the t prime is, we're going to get a negative 1 over root 2, that's going to be a cosine of t I, right? And then we're going to have minus 1 over root 2 sine of t j, and then the last component is constant for t, and so its derivative is going to be 0. Because this is just has it's 1 over root 2 times this vector, which is like a cosine and a sine, this magnitude is always going to be 1 over root 2. So magnitude of t prime, it comes out to be 1 over root 2 always. All right? And so if I scale it down, the normal vector, right? I'm going to write it like this. Normal vector of t, it's t prime of t over the magnitude of t prime at t. This is just to say I'm going to divide this by 1 over root 2, which is the same as multiplying it by root 2. And so this is actually just going to be negative cosine t I minus sine t j. That is a unit vector. And what I want to do now is find the cross product of t and n. The binormal vector is t. I'll be a little bit more explicit with the parameters t cross n. Let's figure this out. So we have I, j, and we have k. We have the t vector is, we have negative 1 over root 2 sine of t, negative 1 over root 2 cosine of t, and then we have 1 over root 2. Now for the normal vector, we have negative cosine t, negative sine t, and we have a 0. Okay, so we're going to have I times, so it's negative 1 over root 2 cos t times 0, which is 0, minus negative 1 over root 2 sine t. That's negative 1 over root 2 sine of t, but that's negative negative, so that makes it a positive. Okay, now it's going to be minus the j vector times, what do we have? We have negative 1 over root 2 sine t times 0, which is 0, minus 1 over root 2 times negative cos t. So this is minus 1 over root 2 cosine t. But that's minus a minus, which makes it a plus, right? And so then the last one is going to be plus the k vector times, what do we have? We have negative 1 over root 2, negative, which makes it a positive, 1 over root 2 sine squared of t, minus times minus, which is minus, minus is plus, let's make it clear, minus negative 1 over root 2 cos t times negative cos t. So that becomes minus a minus, which is plus, okay, but it's 1 over root 2 cosine squared t. Well, not going to simplify this anymore. It's enough to just to look at this and say, okay, well, that's the binormal vector for any time t. So if you have this space curve going along, right? At any point along it, point P, the plane that is determined by that point and this normal vector is it is going to be called the normal plane. And if you can sort of picture this, it might be a little hard to see, but I'll try to draw it. Where we have actually, like, this is going through it, and this is meant to show. It's like a plane that the curve is piercing through at a right angle at any given time. That's the normal plane, and so the tangent vector, the unit tangent vector, is going to be the normal vector for that plane. Like that would determine the equation for that plane. So the plane with normal vector B at point P is going to be called the osculating plane. So what I'm trying to say is, if you have this, so you have this curve, and at point P you've got the unit tangent vector and you've got the normal vector, and as I said, t cross n is going to give you a third vector, which in this case you have to kind of imagine it you kind of have to imagine it kind of coming out of the page, and so it makes the right angles with both of these. What's happening with this third plane, this is the binormal vector. So the plane that's normal to that, which contains both the normal vector and the tangent vector, those are both on the plane. This is a plane which contains, like at this moment right here at point P, the curve lives on that plane. That's called an osculating plane. Of course, as you move around the curve, that plane is going to tilt, and shift and move and stuff. But the idea is it's at that moment the curve is moving on that plane. That's called the osculating plane. So, given these ideas of this normal plane and this osculating plane, actually, if we think of on the curve C at point P, if we try to define a circle that lives on this plane, and it has the same tangent as the curve at P, and if the one that lies on the concave side of C, that's in the direction of n, has a radius of rho is 1 over kappa, 1 over the curvature, that's called the osculating circle. So let's show you what I mean. So I'm going to, let's suppose that I'm drawing this on at this moment we're like on the osculating plane. So this is my point P, right? I'm going to draw the tangent vector is right here. So this is my tangent vector, and my normal vector is going to look like this. We've got the normal vector is Oh, you know what? I feel like I might not have enough room. I'm going to fudge things a little bit. I'm going to move this down. Okay. Okay, so the idea is if you go out a distance of let's just say it's here, where this distance is 1 over the curvature at this point, and define a circle with that center and that radius, right? Oh, I'm doing a pretty sloppy job, but anyway, this circle is going to be tangent to the curve at that point, and this circle is going to have it, so it has this curvature on the radius of the circle. The curvature of the circle is kappa. This circle just kind of describes how like the curvature, like how the curve C is behaving near point P, and so you can actually graph like the osculating circle going along some curve. I'll demonstrate that. Okay, so I'm trying to show here what we have is a curve that's going through space, and at this point you have this osculating circle. Maybe I'll put it like here. So you can see if you go out in the direction of the normal vector, which is blue here, you go out, you can, as I move along the point, that you can see the osculating circle changes in radius, and as we move around, it gets bigger when the curvature is lower, right? The lower the curvature, the smaller the osculating circle, and the plane that it is on is shifting as we move along. Okay, so it's like this. It's like you can think of it kind of like if you're going along in a roller coaster, the top of the track is like going in the direction of like the normal curve. Well, it's not always the case for a roller coaster. I mean, but this could be the case. If you want to be feeling the force of acceleration, always you can think of, well, which side of do you want to be sitting on the side of the normal vector or the opposite one? Anyway, I guess what I just wanted to illustrate is this osculating circle and like what it looks like as we go along the point. But you can see that the tangent vector is red, and that is always pointing in the direction of the curve. The normal vector is yellow. Oh, sorry, the blue vector is like how in the direction in which the tangent vector is about to change, is like changing, right? And then the yellow vector is this binormal vector. Use that to define this osculating plane, find the center of the osculating circle. I don't want to spend much time on that. It's just an application of this that is useful in certain engineering applications. All right, well, we're going to wrap it up there, and we'll do some of this stuff in class. All right, bye.